The experimental videos are quite important so that you can put your theoretical knowledge to the test and apply it in the real world and see that life is not as simple as the theory that you've covered. So in year 8 we did densities to show which minerals come up, and the previous video we looked at periodic table trends so we could tell the mineral groupings. So this one's a lot harder because it's going to look at far more complex principles like the VSEPR, the three-dimensional structures. It's going to look at the bonding, not just the ionic, covalent, metallic, but also the intermolecular forces. And we're also going to touch on the enthalpy bonds and a few other concepts to try and make sense of why these 10 minerals have different scratch abilities. So what I said before, you have covered all these bondings, and then the other thing that's going to be big on this is the coordination number. So how many bonds each element forms with the other one next to it, and also how uniform the material is itself, and the uniqueness of the different structure of the material. And what I'm going to do in this video, and what you're going to do, is you'll scratch the glass, because the glass will be the standard for most tables. It's either less than 5, greater than 5. And we'll also scratch the one below and above it to see whether it's in the right order. So my favorite one to start with is the stuff that's easiest to get your handle of. And obviously that's quartz. And so quartz is everywhere because it doesn't break down. Now, this one's actually I think this one's an alpha. It's spinning either clockwise or anti-clockwise. It could spin the other way. But there's many structures of quartz. And so it can also, I like to compare it to sort of the diamonds one here, where it's in this bond in here where it's all bonded to 4 others. And so in this one here, I've just taken it as possibly on the edge because you're scratching it just to form in the surface. And maybe that would take about that much energy to break. So this is, for me, this one's the standard. And each silicon's bonded to 4 other bonds in a covalent bond. And so that will give that a value of 7. Now the next one I'd like to go to is diamond. Now diamond is the same in that everything's covalently bonded. And so potentially it's a higher energy, but remember this enthalpy is converted to gaseous atoms, and we're not doing that. We're just deforming the surface. And why is diamond so much better? Well, there's not a difference. It's all exactly the same element, and so it's all perfectly even. And so that makes it better than this silicon dioxide here because it's more uniform. And there's less flexibility. And so when you try and move one of these, you're not just breaking these side bonds or getting some flexibility, but the entire structure is going to push back because it's all even and equal. So it's all supporting each other. And so that makes diamond the hardest material of all of them. Now, very similar to that, to silicon dioxide and diamond, is the one that's second highest, the 9 value, corundum. Now, this one is similar to silicon dioxide in that it has 2 different elements there, so it's not as good as diamond, but it's stronger than quartz in that it's got coordination of 6 and then 4 for the other. So it's got extra bonding in there, so that the ionic and covalent bonds are reasonably similar. They're both quite strong. And you can see there that number is quite high if we were to take an enthalpy, lattice enthalpy of dissociation, which means just break it all up into gaseous atoms. And so it's completely like diamond in that the whole thing's ionic bonds as opposed to whole thing's covalent bonds. But it is not as good as diamond in that it's got a variation in its structure. Now, if you go in between quartz and corundum, you get something that's in between the two of them. You get a mix of covalent ionic bonds. It's sort of a hybrid. It has a higher coordination number than silicon dioxide. So there's like 6 on the aluminium, but it doesn't have the symmetry of the quartz or of the diamond. So it's sort of in between on those factors. And so that would make a weaker lattice that can be more easily deformed when you try and scratch it. Now, going down from quartz, quartz is sort of like the perfect crystal where they're all lined up with as many bonds as possible. When they form feldspars, sometimes these positive potassium or other cations can get into the lattice with all these negative oxygens here. And so that just makes holes in the lattice and a weaker lattice. And so, of course, feldspar is slightly weaker than quartz. And just to go down to the standard, glass is amorphous, it's not even crystalline. So there's open ends on the structure everywhere and some random calcium and sodium atoms in there as well. That's how they make the glass. So you can see just a degrading of the crystal lattice of silicon dioxide. So that makes it easier to understand the 7 to 6 to the glass, which is 5.5. Now, going up from the bottom is also nice and easy to understand this one, because you have these very strong covalent bonded chains here. Well, they're actually sheets. But the problem is what's linking the sheets together is nothing. There's only oxygens there. So that's temporary dipoles. So there's only weak London dispersion forces. So that makes them very weak, 0.1 to 5 kilojoules per mole between these sheets per bond. And so it's very easy to slide them per mole of bonds, that is. All right, and then if you move up to number 2, it's sort of the same thing. You have these sheets, this time they're ionic, but ionic and covalent bonds can be quite strong. And instead of London dispersion, you've got these hydroxyl groups here, so these pos and neg permanent poles. So that's the strongest of the dipole bonding, which is hydrogen bonds, which is like about 10 to 40. And so that what makes it significantly harder than, makes the gypsum significantly more harder than the talc. Now, interesting, if we just jump to 4, if you look at this one here, there is quite a high lattice dissociation energy. So it is quite a lot of strong bonds between them. And they're ionic as well, so they're quite strong as well. So what's unique about this is because it's all ionic, you only need a little bit of energy to push it to one edge, and then they're all repelled by each other. And so it makes it actually brittle. And so it's easy to scratch the surface of it. It may be difficult to turn it all into gaseous ions, but because of the way the structure of an ionic lattice is, it's quite brittle and it's easy to scratch. And so for that reason, that's why calcite is number 3 and also easier to break. The lattice is not as tightly held together. There's huge lattice energy, but the structure is in such a way that all the positive calcium ions align and the carbonate negative ions also align. And so the ionic bond between them is quite weak. And you can actually just cleave this quite easily into rhombic crystals because of the way it's structured and it all lines up. So you can see that the way that the atoms just happen to be aligned in the crystal structure can have a huge influence on how easy it is to deform the surface. Even if the other factors say it should be very strong because it's all ionic bonds, huge lattice enthalpy, etc. That just happens to be the 3D arrangement that it lines up, so it has that brittleness to it. And this is another one that sort of you would think would be complex as well. I just put that in for completeness to let you see metallic bonds, because this is all about bonding and applying it to the real world and seeing how it works. The metals can form different types of lattices. So you've got simple cubic, body-centered, face cubic. And this one's actually face cubic, so that the each copper atom is actually within a distance that's close enough to have a bond with another 12. And so it's got a huge lattice enthalpy, trying to get that to a gaseous state. And so you would think, wow, that must be super strong and hard to move a copper. But because it's a metallic bond and the actual cations floating in a sea of electrons, they can actually slide over each other, and it's super soft. It's only 3.5 just to deform the surface and just to push it around a bit. So that is quite unique as well. And so lastly is the hardest one. This is in the too hard basket. I can't make sense of getting a decent structure out of this. It has basal cleavage, so it does line up, so it does chip and scratch quite easily. I'm thinking, why would you choose this apatite? I think Mohs was just biting rocks with his teeth to see where they scratched, or scratching his own teeth. I think that's where he's getting it from, where he had a bone around somewhere. So that's hydroxyapatite. And so, they just out of curiosity, they did discover that certain populations that have fluoride in the water didn't have any teeth problems. And that was before they knew the structure. So now that we know the structure, you can see that if acids are attacking your teeth and taking the hydroxides out, if you put fluoride in, it will replace it and then make it restore the strength back. But they worked that out just by experiments, not by knowing the theory and applying that. The theory came later of how of understanding that iron actually replaces it to strengthen your teeth. Okay, so hopefully that makes sense to you, and you can apply that sort of understanding to a random chemical, and you can predict whether you think what the hardness of that chemical is.